In this video we're going to go over M1 Edexcel June 15. The first question is a momentum question, fairly standard question. Conservation of linear momentum. Momentum before equals momentum after. I do find it helpful to do a diagram here. It talks about two particles P and Q which are going towards each other in opposite directions, it says. It gives us the masses of these M and Km. Here M and Km somewhere, there we go, M, Km, it tells us that. It also tells us the speeds before and after effectively. It tells us everything really. So it tells us the speed of this is 5u and the speed of this is u. That's our before situation. So afterwards, we've got them going in the opposite direction because it tells us again they both of them have been reversed. Each particle is reversed, and that the speeds is half. So it's 5u over 2, and this is u over 2. Again, m and km. So we need momentum before. Let's take everywhere in this direction positive, of course. So we have m times 5u. For this one, making it positive, whereas the other particle Q here is going in the opposite direction, so that's minus Km times U equals to, this is also going in the negative direction, the particle Q afterwards, so that's minus m times 5u over 2. And this is going in a positive direction, the Km one here, so that's plus Km U over 2. Okay, so that's our equation. Quite a few things cancel here, so we can see that M cancels and U cancels also. Okay. So we've got that cancelling going on. Multiply, just rewriting that with what after all the cancels. So that's 5 minus k is equal to minus 5 over 2 plus k over 2. Right, okay, so let's double everything. 10 minus 2k is equal to minus 5 plus k. So that gives us 3k equals to 15, k equals to 5. Okay, so that's the first bit. And the second bit is about impulse. It talks about a magnitude of an impulse. Right, so magnitude of impulse means we're not too concerned about the sign, but we need to be careful when we're working it out. I'm going to use the formula I equals mv minus mu. We can actually use this on either p. We're either going to consider the p before and after, or we could alternatively consider the Q before and after. But I'm going to work with P. So let's just have that. Now the final is minus 5 mu, so it's minus m, so it's m times by 5u over 2, because it's going in the other direction. Take away mu times m times 5u. That's for this particle before. This is momentum before. This is momentum afterwards here. Now that becomes minus 15 over 2 mu. But be careful, because it asks for magnitude, so that gives magnitude of impulse can call it mod I if you like, is 15 over 2 mu, and the mark scheme specifically says, as it should do, I'm not allowed a negative because of the word magnitude. You will notice, for those of you who looked at the mark scheme, they didn't really do it like this. They went directly to just reverse the signs of this, and they've written m times 5u, take away negative m times 5u over 2, because they've just looked at change in momentum, and that they've changed it the other way around simply because they knew that, or we know that it's just looking for the magnitude, so they fixed it so that we would get a positive at the end, which of course is fine, and you're welcome to do that. I just didn't want to get too mixed up with the signs, so I just went with the standard formula here. Had we chosen to do, well, I might as well do that, just for those of you who might have done it this way. Had we chosen Q, the change of momentum of Q, we would have got this. Obviously you don't have to do it twice, but if we used that, we'd have I is equal to mv minus mu, and that equals 2. Now in this case, the final velocity is u over 2, and that is positive, so that's K, the mass is 5m, so it's 5m times by u over 2, take away 5m times by, take away negative 5m times u, and we would have got 15mu over 2. We obviously don't need that, but that can be used as a check. So if we've chosen to apply the impulse equation on Q. And the reason why we had two different signs here is because, of course, the impulse on, as we look at P and Q, the impulse that's applied on P is in this direction, whereas the impulse applied on Q is in this direction. So which is why we got a positive answer when we've applied it to Q, but a negative answer when we applied it to P. But because we wanted positive magnitude, we had to give an answer as positive in the end anyway. Okay, so that's question 1 done. Question 2, just a simple motion, vertical motion using Chauvet. We've got U is equal to 19.6. We've obviously got A is equal to minus G, or minus 9.8, and we want to find the greatest height, and that seems to be about it, apart from the fact that we're at the greatest height we know that V is equal to 0. So we can use V squared equals U squared plus 2AS, which gives me 0 squared is equal to 19.6 squared minus 2 times 9.8, that's negative G. I've changed the sign here to negative because I've got negative G here, times by H, which is our maximum height. So that gives me, when I rearrange, H is equal to 19.6 squared over 2 times 9.8. You can actually see without a calculator that's 19.6 squared over 19.6, so that's 19.6 meters. Okay, so that's the answer to part A. Part B, what we're going to do is it says the time that it's above 14.7 meters high. So we want, in fact, what we're going to find is 2 times. We want the time takes to get from there back down again. Okay, but if we apply an appropriate Chauvet equation of motion, with S is equal to 14.7. Okay, then we're going to get two values of t. So S is 14.7, U is 19.6, and then we have t is what we want, and A is minus 9.8, or minus G. So we're going to use S equals ut plus half at squared. Okay, so that gives me 14.7 is equal to 19.6t minus a half times 9.8 t squared. So that, if I rearrange that, that gives me 4.9 t squared minus 19.6 t plus 14.7 equals 0. Right, I'm going to divide by 4.9 because I can see all of these are divisible by 4.9. So that gives me t squared minus 4t plus 3 equals 0. A nice easy equation to factorise, which gives me my two values of t. So that on the way up it's 1 second, and on the way down it will be after 3 seconds, but once the length of time it's above 14.7. So that means above 14.7 for 3 minus 1, 2 seconds. That's it. Okay, it's a nice easy equations of motion question. Okay, question 3 is a fairly standard statics question. Okay, we have a particle which is in equilibrium. We've got the weight coming down is 2g, and we've got two tensions. Let's call this TQ and let's call this TP. Now it's tempting to, the standard way of doing this is to resolve vertically or resolve horizontally, so a mark on the angles. Okay, you would mark on the angle, this angle here is 35 degrees and this angle here is 55. We can see that because of angles in the respective right angle triangles here. And we can just resolve vertically and we get TP cos 35 plus TQ cos 55 is equal to 2g, and we also get, resolving horizontally, TP sin 35 is equal to TQ sin 55. And then what we have to do is eliminate. If we go, we'd have to have TP is equal to TQ sin 55. Need to be very careful because it's going to be a bit untidy, sin 35. And then what we would do is sub for T. Or the other way around, of course, you could sub for TQ if you wanted the other way around. Okay, which is fine. That's probably the most obvious way of doing it. But there is a little, for this question, because the two forces are at right angles to each other, there is a neater way, a quicker way of doing it. So we'll go with that. That's at right angles. We can see that because these two add up to 90. Okay, so we can actually resolve along either of the, any two perpendicular directions are directions we could resolve along. Now, if we look at the angles that we've got here, obviously this is a right angle here. We've got an angle of 55 here, so that's 35. So this angle is also 55 degrees there. You can play with the angles to justify that to yourself if you want. And then this angle here must be 35 degrees here. So what we can do is resolve along RP. So any two perpendicular directions. Now the beauty of doing it this way is that TQ is not going to come into my equation at all, and I'm not going to have a simultaneous equation. So all I'm going to have is the component of the weight, which is 2g, in that direction. Now, because it's next to the marked angle that I've got here, 35, I can just say that that's equal to TP is equal to 2G cos 35. Okay, and the horizontal, this component here doesn't come into it because it's perpendicular to it. Okay, and that will give me will give me the answer 16 newtons. So it's much quicker than doing all of this. And then if I resolve, let's get rid of that bit then. If I resolve along RQ, okay, along RQ, which is along here in this direction, now I'm not going to get TP in it because it's at right angles to it. And so I will get this component here. Because I've marked two angles, I don't normally do that when we do resolving, but we might as well use cos for both of them. So that this angle here, this component here is 2G cos 55. Okay, so that gives me, that's TQ is equal to 2G cos 55, and that will give me the answer to two significant figures, 11 newtons. Whilst we're on this, I might as well say that with these answers, we want to give 2 or 3 significant figures when G. If you look on the paper, it says where G is concerned, use 2 or 3. I've given 2 here. And in general, an appropriate degree of accuracy is normally 3 significant figures, as far as M1 is concerned. Okay. So that's question 3 done. Let's have a look at question 4. Okay, a lift question. We've got something inside a lift, and this lift has got air resistance. I think somewhere it says upward air resistance of 150 newtons, and it tells us a few things. Also, unusually, well, they do tend to like to change the context of the question. It gives a normal reaction of the magnitude of the force, and I'm going to use that first of all and not work with the air resistance here, because if we look at the forces on the 55 kilogram block itself, there will not be air resistance on it because it's inside the lift. So we don't have to worry about the air resistance bit and all the forces on the lift as a whole. If we look at forces, let's do a little diagram. Forces on 55 kilogram mass. Okay. What we've got is its weight, which is 55G, and the reaction force pushing up on it. Let's call it R, or we wouldn't have to call it R because we don't know what it is. 473 newtons. Right, now we need it descends vertically with constant acceleration, so it's accelerating downwards. So if we apply F equals ma in the direction of the acceleration, we have 55G minus 473 is equal to mass times acceleration. And the mass of the thing is obviously 55 times by A. Okay, so taking G as 9.8 as we always have to, and working out the left hand side, we get 66 is equal to 55A. So A is 66 divided by 55, which is 1.2 meters per second squared. Okay, so not much to do, but you need to be clear in your head about what forces are acting on each individual particle. For part B, again, it would probably be better to consider whole system. We could consider the lift alone, but if we did that, well, then we would, if we considered forces on the left, we'd also have to consider the 473 newtons on the left. as well as its weight. So why not just combine the two weights together? Then we don't have to have the reaction force in there at all and don't get too confused. I probably shouldn't have mentioned that because they've probably confused some people already, but never mind. Consider the whole system. Then we've got a combined mass of 255 kilograms. So we've got 255 G, okay, is the weight of the thing coming down. But we've got a resistive force of 150 newtons. So that's going to be pushing upwards. But of course we've got to count that we're going to have something making this thing not fall. So we've got our tension in the cable that's up there. So we've got two forces going upwards and one going downwards, and it's accelerating downwards. Now we know it's 1.2. So we're going to do F equals ma in the direction of the acceleration. So that's 255 G downwards. Take away the air resistance upwards. Take away the tension in the cable that we wanting to find, is equal to the mass of this whole thing, which is 255 times by the acceleration, which is 1.2. Okay, so when we work all that out, we get T is equal to 255 times 1.2. Let's just put it all up. 255 times 1.2 minus 2. Well, it's just rearranging it the wrong way around. No, that's the wrong way around. 255G minus 255 times 1.2 minus 150. And if we work that out to two significant figures, we get 2000 newtons. To three significant figures, which is also acceptable, 2040 newtons, which is the correct answer, or 2000 newtons, which was what was accepted there. Okay, so that's the first 4 questions done. Despite waffling on a bit, it's still only taken 22 minutes. I think I will adjourn to part 2 for the next 4 questions. Okay, thank you very much.